Chapter 5, called Work and Energy, is concerned with three topics: work, kinetic energy, and potential energy. Now, in part 1 of the introduction to Chapter 5, I went over work and kinetic energy. So this is part 2 of the video on potential energy. And that will lead to the law of conservation of energy. And there's a final section called power. So, first of all, what is potential energy? Well, let's just recall from part 1 of the video. Kinetic energy is the energy of motion. And in particular, if you have a particle or an object, a sphere, could be a small object, anything with mass m moving with velocity v has kinetic energy. The kinetic energy is equal to 1/2 mv squared. A particle with mass m and velocity v. Now, of course, velocity is a vector. But this v is not a vector. This v doesn't have an arrow over it, therefore it's not a vector. That's the magnitude of v. So it's the speed. So the kinetic energy depends on the mass and the speed. Nothing related to the direction of motion. So v here, without the arrow, is a scalar. It's the magnitude of v vector. The vector has a magnitude and a direction. The magnitude I'll just write as v. The magnitude of velocity is speed. Now, the work kinetic energy theorem relates work and kinetic energy. The change in kinetic energy is equal to the work done by the net force acting on m. So the change of kinetic energy will be the kinetic energy final value minus the kinetic energy initial value. So m over 2v squared minus v0 squared, where the particle starts out with some speed v0. After some period of time, it has a speed v. Then the change of kinetic energy is m over 2v squared minus v0 squared. And according to the theorem, that's equal to the net force, the work done by the net force acting on the particle. So, in other words, it's the sum, if the net force depends on position, it's the sum of the net force times the displacement. Well, that's really the formula for one-dimensional motion. So a particle moving on one dimension with a coordinate x, it'll move from some initial position x0 to some final position x. If the force depends on x, is not constant, then you have to divide the interval from x0 to x into an infinite number of infinitesimal parts, calculate the work done on each infinitesimal part, and add up all those little tiny contributions to get the final work. But the important point is the force that's going into this equation is the net force acting on m. It's not equal to the force that m exerts. It's not equal to some other kind of force. It's the sum of all the forces that are acting on M. Now, in one dimension, that's just the sum of the forces. In more than one dimension, that would be the vector sum of the forces. All right, so that's already covered in the part 1 of the video. Now we come to potential energy. For certain forces, there exists a corresponding potential energy function. Not for all forces, but for some forces, and for many of the forces that we're interested in, there's a potential energy function corresponding to the force. Those forces are called conservative forces. So, for any conservative force, in general, it's a vector function of vector position, f of x, there exists an associated potential energy function, and we'll use the letter U for potential energy. That'll be a function of the position of the particle, and it will be a scalar. All right, so write that in your notebook. We're going to have to figure out how you calculate U if you know F. Or, the converse, how you calculate F if you know U. Now, as I say, not every force has an associated potential energy function. Only certain forces have a potential energy function. Those are the forces that are called conservative forces. So, before we can use this, we have to find out what is meant by a conservative force. And then, once we've answered that, what are the equations that relate the force F, which will in general be a function of the position of the particle that the force is acting on, and the potential energy function, which will also be a function of the position of the particle. So first of all, what is meant by a conservative force? F of x is conservative if the work done by F when the object on which the force is acting moves from some point x equals A to some different point x equals B does not depend on the path from A to B. So let's consider a two-dimensional system with coordinates x and y, and a point A, looks like that's 2, 2, and another point B, looks like that's 9, 9. And there's some force acting on the mass, and the mass is moving from A to B. Now for F, this force doesn't have to be the net force. This is just some force. There may be more than one force acting on the mass, but I'm just considering the properties of one of the forces that is acting on M. Now, as M moves from A to B, there'll be some work done. Because remember, work is force times displacement. Or for a force that's varying in position, It's the sum of all the infinitesimal contributions to force as you divide the motion into an infinite number of infinitesimal small displacements. Now, F is not necessarily the only force acting on the mass that we're talking about. It could be other forces. But we're only considering the work done by that one force, F. Now, depending on what forces are acting on M, I keep referring to M as the object on which the force F is acting. Depending on what other forces are acting on M, it can move from A to B in an infinite number of different ways. It could just move straight from A to B. Or it could move along some curve, which starts at A and ends at B. Or it could move on some curve which goes around this way. Or it could move along some curve which goes up and then comes back down and goes up again. There are an infinite number of curves, one number of ways that the mass M, here's M, could move from A to B. So this will be one way, this will be another way. The displacements, well, the final displacement is the same for all curves that start at A and end at B. The final displacement will just be B minus A. But the sum of infinitesimal displacements from A to B can be very different. F is a conservative force if the amount of work done by that force as the object moves from A to B is the same for all the possible paths from A to B. So, if this is in 3 dimensions, or let's just say 2 dimensions, then the work done over a small displacement, let's say delta x, it's in 2 dimensions, so it'll be a vector. Delta x vector is fx delta x plus fy delta y, the dot product. The work done along this red curve will be the sum of all the little infinitesimal displacements in going along that curve from A to B, fx delta x plus fy delta y. And the work done as the mass moves from A to B along this more complicated path will be the sum of all little displacements along that blue curve, fx delta x plus fy delta y. For a conservative force, the two calculations of work will be equal, even though the particle has moved over a completely different set of points, and the force is changing as it moves from A to B, because the force depends on position. The final answer for the work done in moving from A to B does not depend on the path from A to B. It's the same for any 2 paths that go from A to B, or any of the infinite number of paths that go from A to B. That's what's known or called a conservative force. Now, you'll have to read about this in the textbook, but this is meant to be just an introduction to Chapter 5. So this is sort of meant to get you started with the ideas, but then you have to read about it in the textbook. Now, I've described conservative forces in, well, 2 dimensions here, but it would be the same idea in 3 dimensions. One-dimensional motion is simpler. One-dimensional motion, if you have motion on a line, just not moving around in a plane or in a 3-dimensional volume, but just moving along a line, then it's a much simpler situation. Then f of x is conservative if it depends on x, but not on v. So for one-dimensional motion, if a force depends only on the position, not on the velocity, then it is a conservative force. So for one-dimensional forces, it's a very simple thing to know. Here are some examples of conservative forces. Gravity. Gravitational forces are always conservative forces. Spring forces. The force exerted by an elastic spring. Suppose you have a mass connected to the ceiling by a spring. So down here is the mass. And here is a spring. Here's the ceiling. That mass is subject to 2 forces. There's gravity pulling it down. So maybe I'll put the forces in a different color. So that's a problem where there are 2 forces. There's gravity pulling it down. That's always directed towards the center of the Earth. And there's the spring pulling it up towards the equilibrium position. You know, there's some equilibrium length of the spring. If the spring is stretched, then it pulls back. It pulls back in the direction of the spring. So maybe, I don't know, maybe this is the equilibrium length. The spring is stretched. Well, it'll be pulling back. It'll be pulling in this direction, parallel to the spring. Those 2 forces, gravity and spring forces, are conservative forces. Electric forces are conservative forces. But here are some examples of non-conservative forces. Frictional forces are not conservative. Now, if we just consider motion along a line, suppose we just consider motion along a line, like a line on the floor and some mass moving along that floor. So the mass is moving this way. So there's the velocity vector. This is the mass. But there's friction. So there's a frictional force. The frictional force will be in this direction. Opposite to the velocity. So you see, the frictional force depends on the velocity, at least in terms of direction. If the velocity is to the right, then the frictional force will be to the left. But if the velocity were to the left, then the frictional force would be towards the right. So the friction force will depend on the velocity, even in one dimension. Well, in one dimension, a force is conservative. It depends on x, but not on v. Well, this force depends on v. And of course, the frictional force might also depend on how large the speed is. If you think of a frictional force with the air, what's called air resistance, the air resistance force will be larger for larger speeds. So in that way, again, a frictional force, air resistance, would depend on velocity. Any force that depends on velocity is non-conservative. There are some magnetic forces that depend on velocity. The magnetic force on a moving charged particle, like a proton, let's say, depends on the velocity of the proton. So that's not a conservative force, because the force depends on the velocity. Many aerodynamic forces, I already mentioned air resistance, many aerodynamic forces depend on the speed, like lift and drag. Drag is air resistance. Lift is the upward force that causes an airplane to fly. An airplane can't fly if it's not traveling fast enough, because the lift force has to be large enough, and it depends on how large the speed is. So that's not a conservative force. All right, so this is sort of defining what is meant by a conservative force. Now, how do we define potential energy? All right, so let's say there's a conservative force acting on a mass m. This might not be the only force acting on m, but it's a force that acts on m. It could be the only force acting on m, but not necessarily. And let's suppose it depends on position, but not velocity. So there's a force, and depending on where the mass that it's acting on is located, it'll have a different value of force. So we have some m, we have some space, set up coordinates x and y. M is at some point in that space, and when m is at that point, let's say the force is, I don't know, this way. Force is a vector, so it has to have a direction. Well, let's say it's in the negative y direction. And it has to act on something. What's it acting on? Well, it's acting on m. So there's m. If F is a conservative force, then there is a corresponding function, u of x, called the potential energy function. F is a vector, u is a scalar. And this is one way of relating the force and the potential energy. The force in the x direction, the x component of the force, is the negative of the rate of change of potential energy with the x coordinate. So, in words, the rate of, because of the minus sign, it's the rate of decrease. So, in words, the rate of decrease of u with respect to x is equal to the force in the x direction. Now u is a scalar, so u doesn't have any directionality. But the space is three-dimensional in the most general case. So I can consider the change of the potential energy in three different directions. Suppose I'm at some point in the volume. I can take a step in the direction of x. That would be delta x. I could take a step in the direction of y. So that would be delta y back into the page. I could take a step in the vertical direction. That would be delta z. So here I've set up Cartesian coordinates x, y, and z. X and y are horizontal, z is vertical. I have this potential energy function, which depends on position. If I'm at this position and I take a step in the x direction or the y direction or the z direction, there'll be a change in u. And the change in u divided by the displacement times minus 1 is the force that's acting on the particle when it's at this position. So let me put the force in, I don't know, let me put the force in red. Maybe the force is, I don't know, maybe the force is this way. Well, there'll be an x component of the force, there'll be a y component of the force, there'll be a z component of the force. The x component of the force is minus, negative, of the change in u when I make a change in the coordinate x. Delta u divided by delta x. And similarly, I have delta u, delta y, and delta u, delta z. So you see, the force is a vector. It has three components. It has an x component, a y component, a z component. They can all be different. So F has three components, like any vector. But u is a scalar. That's one way of writing the relationship between force and potential energy. Now again, I've described it in the case of three dimensions. If there were a problem where an object is just moving in one dimension, then it's a little simpler. Then I only have one dimension, let's say the x-axis. Then the force in the x direction is the negative rate of change of the potential energy in the x direction. Now, there's another way of writing this. U at a point x is the negative of the sum f delta x along any path from x0 to x. So we choose some point x0 to call the reference point. We call that the reference point. That's the point where the potential energy is 0. See, this equation doesn't really define the absolute value of u, just the rate of change. In order to give it an absolute value, you have to say what value does it have at some point. Well, suppose we call that point x0. So again, here's x0. And we say the potential energy will be 0 at x0. So we call that the reference point. Now suppose I want, so u, we say u of x0 is 0. So we pick some point. That's sort of up to our choice. You know, we pick some useful point and we say, let's take that point to be the point where potential energy is zero. Now suppose I want to know potential energy at some other point. Let's say this point. Call this point x. What is U at x? Well, it's the negative of f delta x dividing the displacement x0 to x into an infinitesimal, an infinite number of infinitesimal, well, let's not talk about infinities. Let's just say into a large number of tiny steps. So if I want to go to x from x0 to x, I take many steps. Maybe the distance from x0 to x is 1 mile. If I want to go 1 mile, I have to take many steps. Each step is about 3 feet. So I take many steps, and in each step, there'll be a value of the force at that point, and the force times 3 feet will be this contribution to the sum. I add those all together, multiply by -1. That tells me U of x at this point, 1 mile away from where I had the reference point. Now you recognize that this is the work done by what force? The work done by the force F. In going from x0 to x. Because, you know, I sum up the work done over each little step. That gives me the total work done as the mass that the force is acting on goes from x0 to x. That's the definition of the potential energy at the point x. It's the negative of the work done by the force I'm talking about as the mass goes from the reference point to x. So again, let's put it into words. Well, the equations say more than the words, but let's convert the equation into words. Suppose the object is located at x. Then the potential energy, U of x, equals the amount of work that F would do if the object moved from x to x0. It's the negative of the amount of work that F would do if the object moved from x0 to x. But if the object is moving not from x0 to x, but from x to x0, then the amount of work that would be done by F is exactly the negative of the amount of work that it would take to, that it would exert in moving from x0 to x. So to take into account this negative sign, U of x equals the amount of work that F would do if the object moved from x, where it's located, to the reference point. Well, this all sounds rather abstract and mathematical because it is rather abstract and mathematical. Unlike the energy of motion, which has a very simple formula, it's 1/2 times the mass times the square of the speed. Potential energy is defined by the rate of change of the force. Well, the force is a negative rate of change of the potential energy. The potential energy is the sum of small displacements times the force at that position times negative 1. So it's a rather mathematical quantity. Like all the concepts in physics, it's defined by equations. And these equations are a little hard to grasp in the abstract. So we have to look at some examples. Examples of potential energy are given in section 4 and section 5 in chapter 5. So this video is just an introduction to chapter 5. You'll have to go and read chapter 5, and in particular sections 5.4 and 5.5, to see some examples of potential energy. Let's consider a case which you'll see in the book and on the homework and probably on the next exam. An object with mass m on an inclined plane. So I have here an inclined plane. Now the object is moving in one dimension, but in Earth's gravity there are two dimensions that are relevant. There's the horizontal dimension and the vertical dimension. So we'll set up a vertical coordinate, which is y, which points vertically upward, and a perpendicular coordinate x, which is horizontal. And the slope here is the rate of change of y with respect to x. Now, if this slope is frictionless, suppose m is an ice cube, and the inclined plane is icy. So m will slip on the surface with hardly any friction. We just say zero friction. If we set m at this point and let go of it, it'll accelerate down the plane. If I put m at this point and kick it up this way, it'll move up this way for a while, but it'll slow down as it moves upward because of gravity. At some point it'll stop, turn around, and go back down. That's a kind of motion which is best described in terms of potential energy. Because the gravitational potential energy, U, does not depend on the horizontal position, but it does depend on the vertical position. U is equal to mgy. The gravitational potential energy for a mass m near the surface of the Earth is mgy. M is the mass of the object. G is 9.81 meters per second squared. It's the same for all objects. Y is the height above the ground. So this is ground level. That's the reference point. I said the potential energy is zero at the reference point. Well, the reference point is y0 equals 0. So you see, u of 0 is 0. So here, u is 0. But here, u is mg times the y position, the y coordinate. So that's one example of a potential function for a conservative force. The conservative force is the force of friction, is the force of gravity near the surface of the Earth. And the potential energy function is mgy. It doesn't depend on x. Now remember, the force is negative delta y over the displacement. Let's call the displacement delta s. So that'll be the force in the S direction. Well, the rate of change of y in the x direction is 0. Because u doesn't depend on x. If I change x, I don't change u. Delta u is 0. So the force in the x direction is 0. That's because gravity is a force which is downward. Now, the rate of change of u with respect to y is minus mg. So I'll calculate delta u over delta y. Well, that'll be mg y plus delta y minus mg y. So here's delta u. As y changes from y to y plus delta y. Delta u will be mg at y plus delta y minus mg at y. The final value after the change minus the initial value before the change. And now delta u over delta y is that divided by delta y. Well, here the mgy cancels the minus mgy. I have mg delta y divided by delta y. That's just mg. Because the delta y cancels in the numerator and the denominator. So delta u over delta y is mg. That's supposed to be the negative of the force in the y direction by this equation. And you see, that is the gravitational force. The gravitational force on this mass is minus mg in the y direction. So I could draw the force on the diagram. Let's put that in a different color. Let's put that in, I don't know, white. So here's the force of gravity. It's minus mg. Force has to be a vector, so I have to multiply by a vector, times the unit vector in the y direction. I call that j hat. So Fy is minus mg. All right, so gravitational potential energy of a mass m sliding down or doesn't even have to be moving. The gravitational potential energy of a mass m on a inclined plane is equal to mgy, where y is the coordinate, the vertical coordinate. All right, now let's ask a question. Calculate the speed of m when it reaches the bottom of the inclined plane. Let's say it starts at the top at rest. So it starts here, not moving. That's some height y0. If I look at the graph, it's 2 meters. So it starts with y equal 2 meters and x equals 4 meters. And it's not moving. So I'm holding at this point. But again, let's assume that this is frictionless. So there's no friction. It's an ice cube on an icy surface. So it doesn't have any friction. So if I start with it up here, I have to kind of hold it there for a while to keep it from moving. Now I let go. Sometime I let go, it accelerates down to the bottom. And this will be the point where I'm trying to calculate the speed. So the question is, at that point, what's the speed? By the way, Gravity is not the only force acting on this ice cube. There's also the normal force. So let's put in another color. Maybe I'll put this one in yellow. Here's the normal force. Oops, I didn't want that to be black. I wanted that to be yellow. Here's the normal force. Well, that doesn't show up very well. Let's put it in orange. Here's the normal force. Oh boy, let's put this in a different color. Let's put this in orange. Here's the normal force. It's perpendicular to the surface. And there's no tangential force because that would be friction. But there has to be a normal force. Now, I could analyze the motion of M. I'd have to analyze the normal force and the gravitational force. I could say the force perpendicular to the surface, the net force perpendicular to the surface is 0. So n times the cosine of the angle, some angle here, n times the cosine of the angle has to cancel minus mg. The force which is producing the acceleration is n times the sine of the angle. So the acceleration would be n times the sine of the angle. N times the cosine of the angle would be equal to mg. So I could figure out the acceleration. And then I could use Newton's second law, analyzing forces and accelerations to figure out how much did the velocity increase. The acceleration would be g times the tangent of the angle. But I can solve this problem without going through the forces. I can solve this problem just using conservation of mechanical energy. Energy is conserved. The total energy is conserved. Energy is kinetic energy, 1/2 m v squared plus the potential energy, mgy. The law of conservation of energy says this expression is constant. 1/2 mv squared plus mgy is constant as the object moves. As the object moves, y changes and v changes, but 1/2 mv squared plus mgy does not change. Now we'll come back to the conservation of mechanical energy a little bit later in the video, but let's just use conservation of mechanical energy to answer the question, what's the speed at the bottom? Well, 1/2 mv squared plus mg times y at the bottom, well, y at the bottom is 0, is equal to 1/2 mv squared at the top, but v squared at the top is 0, plus mg y at the top. Well, y at the top is y0. So v, well, I can cancel m, the mass doesn't matter, mass cancels out. Multiply both sides of the equation by 2, take the square root, then I get v is 2gy0 square root. It's 2 times 9.81 meters per second squared times y0, which is 2 meters. So inside the square root, I have the units meters squared divided by second squared. Or take the square root, that'll be meters per second. So I'll get the velocity in meters per second, and it'll be, well, approximately the square root of 40. Something a little over 6. Use a calculator at 6.26 meters per second. So you see, I calculated the speed at the bottom without analyzing the forces, but knowing the potential energy function, mgy, and conservation of energy. All right, well, read sections 5.4 and 5.5. You'll see some other examples. Conservation of energy. Conservation of energy is a universal principle of science. All the sciences have a concept of conserved energy. Now, there are many kinds of energy, but they all have one thing in common, and that's they contribute to the conservation of energy. The law of conservation of energy, a unifying principle in all the sciences, says that energy cannot be created and energy cannot be destroyed, but energy can be converted from one form to another. There are many different kinds of energy, and it's possible to convert energy from one form to another, but the total amount of energy is constant. Now, that's a universal principle. It applies in all branches of science. In Physics 231, we're studying mechanics, a particular part of science. In mechanics, we have the conservation of mechanical energy. In mechanics, there are two kinds of energy. There's kinetic energy and potential energy. Well, actually, there are many kinds of potential energy, because for each conservative force, there's an associated potential energy. But all the energies that we encounter in mechanics can be divided into kinetic energy, the energy of motion, and potential energy, the energy of position. So the statement of the conservation of energy in mechanics is this. In a mechanical system with conservative forces, the total energy is a constant of the motion. If there are non-conservative forces, they have the effect of converting mechanical energy into some other kind of energy. So, for example, friction converts mechanical energy into random energies of atoms and molecules. That transfer of energy is called heat. But any loss of mechanical energy, the same amount of energy is given through the process of heat to the atoms and molecules in the materials that are in the system. Now, we'll mostly be interested in cases where the only forces acting are conservative. And then the total energy is a constant of the motion. When I say total energy in this way, I mean kinetic plus potential. So we have some kinetic energy in the system, 1/2 mv squared for every particle in the system. And we have some potential energy in the system, one form of potential energy for each conservative force. If we add up all the kinetic energy and we add to that all the potential energy, that's the total energy, E. Now, as things change, as objects move, kinetic energy will change. When something moves faster, it has more kinetic energy. Potential energy will change. When an object moves uphill, it has more kinetic energy of the gravitational force. So kinetic energy, K, and potential energy, U, will change as the system moves. But E is constant. That fact allows us to solve many different kinds of problems in mechanics, do calculations. It simplifies many calculations to take into account the fact that E is constant. And you'll get many chances to see that in the long kappa homework. Now, this isn't something that goes beyond Newtonian physics. This is just a property of Newtonian physics. In fact, we can prove it. We can prove that E is conserved. It's not just an empirical fact or an experimental fact. It follows from the mathematics of Newtonian mechanics. So here's the proof. I'll give the simplest proof for a single object, say a mass m, moving under the influence of a single force, a conservative force, some force F, with its corresponding potential energy U. Now consider the change that occurs in this system during a time delta t. Remember, we always use this delta notation, where delta, the Greek letter delta, stands for the change of some quantity. So delta t is the change in time. Maybe you're looking at a motion which takes place over a period of, 60 seconds. Then delta t would be 60 seconds. The change in kinetic energy is delta K. And we know from earlier in the chapter, delta K is equal to W. It's the work done by the net force acting on the object. Well, we're assuming that there's just a single net force, a single force, so it'd just be the work done by that force. That's the sum F delta x, where little delta x, lowercase delta x, means an infinitesimal portion of the displacement in x. You divide all the coordinate displacements into small parts, delta x. For each small part, you have a value of the force at the position of that little displacement. F delta x is the amount of work done by the force over that displacement. If you add those works over the entire large displacement, that's the sum, sigma, you get the total amount of work. That's the work kinetic energy theorem. Now, the sum f of x delta x is equal to the negative of the change of potential energy. That's the definition of potential energy. The force is the negative of the change in potential energy per unit of distance. So if I add up all force times distances, I get the overall change in potential energy, the negative, because force is minus the rate of change of potential energy. All right, so delta K is minus delta U. Or in other words, delta K plus delta U is 0. The change of the total kinetic energy plus the change of the total potential energy is 0. There's no change if you add the energies together. In other words, K plus U is constant. If K increases, U must decrease by the same amount. Or if K decreases, U must increase by the same amount. So energy is never created nor destroyed. It may be converted from kinetic energy to potential energy, or in the other direction. So one of these may go down, but the other one must go up by the same amount so that the total is constant. And that's the law of conservation of energy. Historically, this is where energy started in science, with this fact that for a mechanical system, kinetic energy plus the potential energy is constant. And it's not some new principle that goes beyond Newtonian physics. It's just a consequence of Newton's laws of motion. We use Newton's laws of motion to prove that the change in kinetic energy is the work. And we defined the potential energy for a conservative force so that the work is a negative of the change in potential energy. So that's conservation of energy, and this equation, write it down in your notebook, because you're going to be using this equation over and over again in the law and kappa problems for Chapter 5 and for future chapters, and for the next exam. Well, we'll finish this introduction to potential energy with one more example. Calculate the gravitational potential energy of the Earth-Moon system. Now, we learned that gravitational potential energy for an object near the surface of the Earth is mgy. But the moon is not near the surface of the Earth. So we can't use that formula for the potential energy of the Earth-Moon system. The force on the moon is given by Isaac Newton's theory of gravity. The force on the moon is minus g mm over r squared, where capital M is the mass of the Earth. Here's the Earth. Everybody knows the Earth is blue. Little m is the mass of the moon. Here's the moon. I don't know what color the moon is. In sunlight, light reflected from the sun, it's white. So I suppose you could say the color of the moon is white. The distance from the Earth to the moon is some distance r. Really, I should say the distance from the center of the Earth to the center of the moon, these are both spherical, is a distance r. And according to Einstein's theory, Isaac Newton's theory of gravity, the force on the moon is gmm over r squared. It's an inverse square law, times minus 1. The minus 1 shows that it's directed toward the Earth. So the Earth is pulling the moon towards its center. Of course, the moon is not moving towards the Earth's center. It would fall down and collide with the Earth, and that would be a horrible disaster. The moon is moving on a circle. So here's the trajectory of the moon. It's on a circle at a distance r from the center of the Earth. It never comes any closer to the Earth than that distance r. Well, actually, it's not on a circular orbit. It's on an approximately circular orbit To be more precise, the orbit is an ellipse. So sometimes the moon is approaching the Earth, and other times it's moving away from the Earth. On the average, it's just sort of staying at a distance r from the center of the Earth. But I'm interested in the force and the potential energy. Well, the force, put the force in a different color. The force is this way. It's towards the Earth. You know, the velocity of the moon is changing as it moves around on this circle. There's a centripetal acceleration. There must be a centripetal force producing that acceleration by Newton's second law. The force is gravity. That's Newton's theory of gravity. Published 1687, although he figured out the theory quite a few years earlier, just didn't publish it. Now, what's the gravitational potential energy? Well, let me tell you the answer. The gravitational potential energy is minus gmm over r. The force is minus gmm over r squared. The potential energy is minus gmm over r. Why? Well, because the rate of change of u is the force. Well, delta u over delta r, that's the rate of change of r, of u, with respect to r, is the negative of the force. The force is the rate of decrease of potential energy with position r. So let's calculate delta u for this formula. It's minus gmm, 1 over r plus delta r, minus 1 over r. Now we can complete the square in this combination of fractions. So I have minus gmm, r plus delta r times r, and in the numerator, r minus r plus delta r. The r here cancels the minus r. The minus sign here cancels the minus sign in front. So this is gmm delta r in the numerator, r plus delta r over r. Now delta r is supposed to be a small displacement in r. You know, r is a very large distance. Let's say delta r is, 1 meter. And if I compare 1 meter to the very large distance from the Earth to the moon, I can neglect this delta r here. I can neglect the delta r in the denominator because it's added to a much larger number. I can't neglect the delta r in the numerator because that would just give me 0. But I can neglect this delta r. And so what I have is gmm delta r divided by r squared. That's a valid approximation because delta r is much smaller than r. Now divide both sides of the equation by delta r. Delta u over delta r, by the calculation, is gmm over r squared. And that should be minus fr. And it is minus fr because minus fr is gmm over r squared. So what I just proved is that this function is the potential energy for that force. Because the potential energy has to be related to the force by this equation. And if this is the potential energy function, then this equation is true. So this must be the potential energy function. And so the answer to the question, here was the question, what's the gravitational potential energy of the Earth-Moon system? It's negative gmm over r. M is the mass of the Earth, little m is the mass of the Moon, R is the distance, or kind of the average distance from the center of the Earth to the center of the Moon. And G is a universal constant, the Newton gravitational constant. If you look up these numbers in the book, or you look them up using Google or something, calculate the answer is it's negative 7.62 times 10 to the 28th power joules. The unit of energy is the joule. The unit of work is the joule. The unit of kinetic energy is the joule. The unit of potential energy is the joule. So if we think of joule as kind of an everyday unit that you might experience in everyday life, you see the gravitational potential energy of the Earth-Moon system is 10 to the power 28th larger. And it's negative. What does it mean that it has negative potential energy? Well, the reference point is the point where R is infinity. So if we take as the reference point way out here where R is infinity, so if we take R for the reference point to be infinity, that's the point where the gravitational potential energy is 0. You see at R equals infinity, U is minus GMM over infinity. That's 0. So if I take the reference point to be infinity, this has a potential energy which is negative compared to the potential energy infinitely far away from the Earth-Moon system. And that's because the Moon is attracted to the Earth. So as the Moon moves from infinitely far away to its actual distance, its potential energy decreases from 0 down to minus 7.62 times 10 to the 28th joules. You're going to have a number of homework problems where you'll have to calculate potential energies. We'll come back to Newton's theory of gravity in a later chapter. But anyway, this completes the part 2 of the introduction to chapter 5. But you still have to go back and read chapter 5. This is just an introduction to get you started. And then do the Lon Kappa problems for chapter 5.